The stability of nuclei are different, therefore all will decay at different rates. For example, starting with the same amounts of material, iodine-131 decays more rapidly than carbon-14, which in turn decays more rapidly than uranium-238. Now the half-life is a measure of the rate of disintegration of radioisotopes. Each isotope has its own half-life and is unaffected by external conditions. So the half-life of an isotope is the time required for half the atoms in a given sample to undergo radioactive decay. Focusing on carbon-14, it has a half-life of 5,730 years. What does this mean? Well, if we had 10 grams of carbon-14, after 5,730 years, half of the atoms would have decayed into nitrogen-14. So we should be left with 5 grams of carbon-14. But how do we know which atoms? Well, we don't, because the decay of atoms is random, but we know half of them would have changed after 5,730 years. So another half-life passes. Of the 5 grams left of carbon-14, half of those atoms would have decayed into nitrogen-14. This means we would be left with 2.5 grams at this stage, and so on and so on. Check out this graph of this decay. It shows as an exponential decay of carbon-14. I'd enjoy this, by the way. So why all the fuss on half-life? The consideration of radioisotopes helps determine its suitability. For example, radioisotopes that are injected into the body should have short half-lives, like in hours or days, just to help minimize exposure to all that healthy tissue. For example, technetium-99m and iodine-123 are radioisotopes used regularly in medical diagnosis, and their half-lives are about 6 and 13.3 hours respectively, but we'll visit those in another exciting video.